So, hi everyone. It's a pleasure to host Professor Brad Carter from the University of Southern Queensland today. He will tell us about the shared evolution of stars and planets. So, Brad was educated at the University of Queensland, then took his first position at the University of New South Wales in Sydney. He then moved for a position at the University of Southern Queensland, where he has been since 1995. And where he is now the director of its Center for Astrophysics in the Institute for Advanced Engineering and Space Sciences. So Brad's current roles at USQ include coordinating the teaching of physics, astronomy, and science programs and courses, supervising graduate student research in the field of stellar astronomy and planetary systems, leading research and development teamwork at Mount Kent Observatory, which I believe he will tell us about today, among other things. So please, Brad, take it away.
Thank you very much, Valentin, and hello, everyone. I'm assuming that the audio and the video are working fine, but do let me know if there are problems we have to deal with. Okay, so a prelude to start with a very broad brush. I would argue that there are essentially four profound questions that astronomers are attempting to answer these days. Why are we here? Why we have a physical universe that exists with the particular physics we have and we're in it. It's also about, I guess, how do we get here? So it's cosmic evolution, galactic, stellar, and planetary. There's a long and grand story of the cosmic origins of humanity. What's our future? So it's forecasting at the longest possible scales, the future of our own planet, our solar system, and the universe beyond. And then finally, of course, I guess you could describe this question of who's out there. In other words, the grand quest to search for life beyond the Earth, to answer the age-old questions as to what sort of life may be out there, especially if it's intelligent and communicative. So to some extent, this talk really is essentially the astronomy that goes with the final question, though it does relate to the others. So the overview of this talk is essentially spending some time on the science of why you need to know about stars to know about planets, exoplanets in particular. Some discussion of current key projects here at USQ, Minerva Australis and Shared Skies, doing spectroscopy and photometry, supporting the NASA Transiting Exoplanet Survey Satellite Mission, or TESS. A little bit about the SONG, Stellar Seismology Project, that's fairly new to Mount Kent Observatory, and it's about both stars and planets. A little bit on the work we do regarding the GALAR, Galactic Archaeology Project, and how we use it to study stars and hence planets. And then Be Cool, appropriately named magnetic field studies of cool stars and much else to do with them. And then something on some key projects for the future, namely adding the Raptor telescope to the Veloce spectrograph at Siding Spring, and finally Twinkle Space Mission, forthcoming space telescope, and just a few brief remarks on the implications of stellar and planetary evolution for life in the universe. So now we begin, and I think David Ciardi's comments here perhaps are a good argument for why we do what we do at USQ, and that is essentially if you want to understand exoplanets, a lot of exoplanet science is actually stellar astronomy. It's really about understanding the motions of stars or stellar behavior that tells us that exoplanets exist and what their properties are. So in many ways, we are, if you like, doing holistic astronomy, where we are studying both stars and planets as a system and the evolution of the two together. So as David says in his quotes there, everything we derive with regard to the planet, size, mass, atmosphere, is done relative to the star. So quite simply, it's know the star, know the planet, and that's actually been the title of some conferences in recent years. Next slide. Okay, so let's set the scene with our solar system, something familiar to us all. Our sun is at least a second generation star, and of course it formed from a dusty gas with the dusty bits enabling rocky planets to form, including our Earth. We have 8 major planets, lots of smaller worlds of rock, ice, and dust in various concentrations. And of course, the solar system, particularly the inner solar system, is bathed in solar winds and the magnetic fields generated by the sun. as well as sometimes very energetic radiation when the sun is very active. The young sun was a rapid rotator and had a vastly more powerful dynamo, magnetic dynamo, and this meant that the early solar wind was literally thousands of times more energetic, more powerful, more impactful than the gentle breeze of the solar wind today. And so the sun itself and its activity and its winds have tended to be a significant influence on planetary atmospheres in our solar system, and of course, to some extent, limited habitability. We are, of course, in this golden age where the sun is being mostly well behaved, but a billion years from now, increasing solar luminosity due to the fact that the core of ash is piling up and getting bigger, and radiation is getting slightly more powerful for us here on Earth, means that increasing solar luminosity in about a billion years is likely to cause a runaway greenhouse effect, no matter how environmentally friendly we are, sadly. So we live in this long but finite period of planetary habitability here on Earth, controlled ultimately by the sun. So yeah, we can think of habitability as both a time and a place. Next slide. Planets. I'm sure we all know what planets are, so I won't dwell on too much basics here. But of course, exoplanets is a convenient term for planets beyond our solar system, including those rogue planets that are between the stars, interstellar planets. Thousands have been found so far, and I've just put a link in the slides to the tally, which is more than 4,000, I think, at least, and climbing almost every month. And of course, along with individual planets, we find lots and lots of multi-planet systems of great variety. The next slide, stars and planets, a shared history. So of course, stars and planets form together. There is a dusty and magnetized gas. Stellar evolution is relatively simple. Okay, I know there are lots of details and there's some very expert people probably online right now, but I will just briefly note that compared to the stars, the planetary evolution is perhaps a bit more complicated story to unravel. And so planetary evolution depends on, amongst other things, the host star. So what we can conclude from all of this is there are exoplanets in great numbers. Estimates vary, but essentially 100 billion planets is one quote. There may be rather more than that in our galaxy. And of them, of course, 300 million, perhaps billions of potentially habitable worlds in our Milky Way galaxy alone. 10 to the 20 Earth-like worlds, perhaps, in the universe today. And if galactic and stellar evolution pans out as we think, you may well have 10 times that number of Earth-like worlds created throughout the future history of the universe, until such time as, sadly, the last stars die. But that's a whole 100 trillion years away. Probably not something for us to worry about too much today. Okay, when it comes to finding exoplanets, again, most people online probably know the story here, but I'll go briefly through the basics as a reminder, shall we say. Transits are, of course, a highly effective technique for finding exoplanets, and you get planetary radius. And transits, of course, are dependent on a certain amount of luck. You've got to have the stellar and orbital inclinations in a favorable way. If all goes to plan and you're lucky enough, you'll find planets. But there are, of course, many planets that just aren't detectable by transits. Fortunately, of course, there's another way, particularly for nearby planetary systems in our solar neighborhood. The Doppler-Wobble method has been a very reliable technique, and across a wide range of angles of the planetary orbit, we can detect some sort of reflex motion from the host star. So we're measuring, of course, the very subtle baryocentric motion of the star, and what we get, of course, is the minimum planetary mass. We need to know about inclination angle to convert that to a true mass. But essentially, we get a good feel for what planetary masses are just from the observed reflex motion. And of course, the reason is we haven't discovered planets until at least the 1990s was the fiendishly precise radial velocity measurements. So compared to the old days of stellar astronomy, when a kilometer per second precision was fine, these days, even 1 meter per second is so last Tuesday for some people, okay, but that's where we're at. The other thing I'd note briefly is that stellar activity is a pesky nuisance for exoplanet scientists, even though it's a boon for stellar people. And that jitter in radial velocity caused by activity is of interest to some scientists and a nuisance to others. Unfortunately, bringing the two together, as we are trying to do at EOSQ, means that if we understand stellar activity well enough, we can understand the source of jitter and actually correct for it to find planets around even active stars. So, of course, as I mentioned before, exoplanetary systems do exist in abundance. The system architects are, of course, incredibly diverse. So if you look at a textbook from the 1980s, the ideas in those days were, well, you'd find just variations in the solar system, wouldn't you? And of course, no, nature had a very different idea. We have incredible diversity of planetary system architectures. So the solar system is one variation on the theme, and there are many different ways to form planetary systems around stars. We get orbital resonances. So the Titius-Bode law, if you like, very clear for some systems. Perhaps you also, of course, have gravitational interactions. And so you can understand how important planetary migration is in exoplanetary systems and in our own solar system. And of course, in some cases, planets are ejected from the system entirely, which explains why we see interstellar rogue planets. They were kicked out of their home some time ago. We can also do, with multi-planet systems, unlike single planets, we can do a good job of understanding the orbital stability. So dynamical studies of orbital stability for multi-planet systems and showing that the system is stable over long times helps us confirm exoplanet detections. So where we've got to now is, of course, essentially 4 different types of exoplanets. The gas giants like Jupiter, the Jovians, less massive but still gaseous Neptune-like worlds, terrestrial worlds like the planets of our solar system, and unlike our solar system, but surprisingly common out there, are these so-called super Earths. So Earth-like, but somewhat beefier in terms of mass and radius, okay, but still Earth-like in many ways. On to the next slide, exoplanet diversity. What we're finding in brief is exoplanet populations which span the orbital period and size range. You can categorize them as hot Jupiters, unlike anything in our solar system, cold gas giants, which are rather more solar system-like, ocean worlds, hypothesized ocean worlds at least, and ice giants, like our solar system in the latter case, rocky planets like the Earth, and it gets most people excited, and then of course lava worlds would make a great holiday destination for Darth Vader, I gather. If we looked at the basics here, of course, we would assume, just like in the solar system, the snow line should divide warm terrestrials from cooler worlds, but the reality is very different. And of course, the reality means that planet formation below and above the snow line is mixed up with a lot of gravitational interactions, both with the solar nebula, the stellar nebula that forms planets. There's motion of protoplanets as well as motion of the planets themselves. So what we get is a crazy mixed up set of planetary systems. Some are like the solar system for sure, but you get hot Jupiters, warm Neptune, super Earths, and even crazy super puffs, which is a nickname for planets which have an incredibly large radius, not a huge mass, and literally the density of styrofoam, okay? So as usual, nature surprises us by giving us a diversity of planets well beyond whatever we thought by surmising from the solar system. We get tilted rotation planets, retrograde orbit planets, and resonant or near resonant systems, as well as the rogue planets I mentioned previously. So what this means, of course, is the diversity is driven by migration of planets as they form, as well as major gravitational interactions between these worlds. And they're also pretty clear indications that our census of exoplanets is far from complete. So one of the things we're doing at USQ is having the longest time-based observations possible to look for genuine solar system analogues, the Jupiters and Saturns, that we think will be out there in large numbers. So habitable zone planets, of course, are the ones where it's a Goldilocks, right? Not too cold, not too hot, just right for life in terms of liquid water, at least. So there's a plot there on the right that gives you essentially habitable zone planets, but of course, defining what habitable zone means depends on your assumptions about the planet. So there's both an optimistic and a pessimistic habitable zone. No matter which way you cut it, there are still plenty of supposedly habitable zone planets. But I guess one of the lessons we're trying to take to heart at USQ is habitability is not just about being the right temperature. There are other factors. And in our case, space weather, as well as planetary composition are important factors. Just because something is in the right orbit doesn't mean to say it's remotely habitable. Of course, people are studying exoplanet atmospheres, and this is a really new field because it's really hard to do. You thought detecting planets was hard. Wait till you try and detect their atmospheres. So what we're looking at here is looking at the difference between the spectrum of a star plus planet and the spectrum when this planet is hidden, and hence the star. So the difference techniques gives us some idea of the spectra of exoplanets in limited cases where the observations are easiest. Not easy, just the least worst one so far. We're finding, as you might expect, things that are familiar to us: water vapor, carbon compounds. There's also clear evidence at the same time is if you have a planet that's close enough to the host star, it'll be blowing off most of its atmosphere, eroding. So it would look pretty much like a giant comet if you're up close. But we're still in an era where, we're incredibly limited by signal to noise. And one of the best ways to make progress is space telescopes free of Earth's atmosphere, and the opportunity you have for higher signal to noise and all sorts of molecular observations that are difficult, if not impossible, from Earth. And along with that, despite the scarcity of data, it doesn't stop people modeling exoclimates in great detail. So as soon as we have the data, we'll have models of climates and atmospheres to work with. When it comes to surfaces and interiors, again, it's a real challenge. Really, only indirect information is available, and models play a huge role. The models tend to use basic information like mass and radius and temperature, and then you can surmise what might be there. You can, of course, get some idea from the solar system studies. You can also use stellar abundances. But of course, if you wanted to take stellar abundances of the host star and turn that into compositions of the planet, you have to be very clever about understanding the loss of volatile gases due to heating. So you have to know how exactly you get from a stellar abundance to a planetary abundance. And if you're lucky, of course, you get atmospheric spectra of the planet. And that, again, can be some indication of what lies beneath in terms of the surface and the interior. Next slide. Astroseismology is really useful, not just for understanding stellar structure and evolution, but the more you understand the star, and in particular understand the star's basic properties, you can use that information to give the most precise planetary properties. Because whether you're using transits or whether you're using radial velocities, if you observe the star with sufficient precision in terms of transits or radial velocity measurements of the surface of the star moving up and down along the line of sight, that will give you new information on what's inside the star. And so whether it's photometry or spectroscopy, if you have the right equipment, the right observation, the right targets, you get incredible information about stellar structure and really, really precise information on the size and mass of the star. And that in turn means precise planetary and stellar radii. So it's, again, really hard to do, technically very challenging, but if you can do stellar seismology of the host star, you have unprecedented information to understand the surrounding planets. We also, of course, have exoplanetary space weather as an important theme in understanding stars and planets holistically. the so-called solar-stellar connection, which is a term used for literally decades. It's a two-way street. So it's not just about stars, because now once you know more about stars, you know about their planetary systems. Stars, of course, provide proxies for studying solar evolution and its effects. And by the same token, stellar observations are best usually interpreted using models derived from solar physics, where we have a local, detailed, up-close and personal star to understand. Solar and stellar dynamos both, of course, make magnetic activity, winds and space weather. That I think is fairly clear. And again, what is clear is the greatest impact of the star on the planet is when the star is young, rapidly rotating, and a powerful dynamo. So in our own solar system, it's very clear that the young and powerful solar wind was eroding a lot of the Martian atmosphere. Earth was much luckier due to the thickness and the magnetic field we have, but Mars was very much a victim, if you like, of a very powerful young solar wind. So we move on. Okay, let's summarize things. Essentially what I'm trying to do is convince you that it is important to know the star, to know the planet. And we can say that stellar astronomy really is the basis of a lot of exoplanets today. We use observations of stars to discover and confirm planets. We get information on mass and orbit from the motion of the host star. Same with the radius when we're doing photometry of the planet. The density when we know both the radius and the mass of the planet. And from that, we can infer what sort of type of planet we might have from its density, its bulk density. If we're lucky, we can do transit spectroscopy to observe the atmosphere of a planet directly. And of course, we can infer planetary properties from the host star abundances if we're careful, and especially if we have exoplanet spectra, we can get some idea of what the planet is made of. We've seen before that seismology of the host star helps us not only understand the star for its own sake, stellar evolution, but can give us great information on understanding the reality of what a planet is around it. We can use stellar magnetic field studies to infer space weather impacts on the atmosphere and by implication habitability. And essentially all of this together means that we can go from comparative planetology in our solar system to a genuine new field of comparative exoplanetology. And of course, in coming years, we'll see a lot of focus on searching for biosignatures in exoplanetary spectra using space telescopes in particular. Okay, we'll take a break for a moment. And I assume, unless someone's desperate to ask questions, I'll move straight on to part 2, which is about us. So a bit about astronomy at USQ. It's been part of the USQ story since the 1970s. We've had an astrophysics group, which has grown. We have a formal Centre for Astrophysics. We have astronomers both at Toowoomba campus and now the Springfield campus near Brisbane. And I'm pleased to say we have something of a Team Queensland approach to astronomy, and we will have an ASA Queensland Hub Day as part of the ASA annual scientific meeting in July. So in Brisbane, we will have all 3 universities doing astronomy, USQ, UQ and QUT, all hanging out together, which is great. In terms of who we are and what we do, we're very much focused on online learning, though we have now restored some on-campus teaching that we used to have. We offer a set of courses that enable people to study astronomy from the BSc right through to the PhD. We got a good rating, the best rating, in fact, of 5 from the ARC ERA review in the most recent round. And right now we have 6 academics and 5 researchers. And I'm pleased to welcome George Zhao from Harvard Smithsonian Center for Astrophysics and Chelsea Huang from MIT. They're both joining us as ARC DECRAs this year. George has arrived and Chelsea is on her way. We also have a cohort of both on-campus traditional students and a lot of online research students who I'm pleased to say for the most part are doing pretty well doing research online with us. We have some involvement with Siding Spring through the AAT, and of course we're part of the consortium involved with the Veloce spectrograph project at Siding Spring, and as well as Galar. Mount Kent is in the Darling Downs, so it's away from the Toowoomba Range. It's got better weather than Toowoomba has, which is good for astronomy. The site's been in use for some time, at least the 1980s. We actually jointly opened the facility with UQ in 96, but USQ ended up leading further development in the 2000s. We've had a partnership with University of Louisville since the early 2000s, a great big expansion of Mount Kent facilities in the last few years. And I would argue we have quite an interesting special observatory now in Queensland doing all sorts of astronomy that I'll tell you about shortly. We have a Centre for Astrophysics, so we're part of something called the Institute for Advanced Engineering and Space Sciences, and that more broadly is about aerospace and space composites, hypersonics, and of course astrophysics, so a really interesting combination of space sciences and engineering. What we are supposed to do, shall we say, we are supposed to use the Centre to enable stellar astronomy and planetary systems research. We're not limited to that, but that's mostly what we focus on. We often use global or domestic Australian facilities for that beyond Mount Kent, but we also do a lot of work at Mount Kent. Having our own observatory is very handy. We also use a HPC, which has recently been upgraded, I'm pleased to say. And finally, in tune with the zeitgeist of the age, we are very much involved in space stuff now, and with some connections to the Australian space industry that is growing. Okay, so again, won't dwell long on this slide. I think you probably get most of the story. We're into stars and planets. Effectively, we do exoplanet science and stellar magnetic field studies, activity, and bring them together to help with discovery and characterization of planets, do space weather studies, study the effects of space weather and more general stellar effects on planets, and of course, we hope in some small way, help to inform the search for habitable worlds beyond the solar system. A lot of what we do involves, of course, support for the TESS satellite, the NASA satellite, and using Mount Kent Observatory. Next slide. I won't dwell long on this. You don't have to memorize it. There won't be an exam after this, I promise. But just to give you a flavor of what we do, we have Minerva Australis doing exoplanets. We do shared skies stuff, there's stars and planets. Song is about stars and planets. We also actually host a SmartNet German space agency, GSOC, space debris monitoring telescope, setting up meteor cameras for the Global Fireball Observatory. We're part of the team behind Veloce, a spectrograph at Siding Spring. Have a new project to value add to Veloce with a new telescope. We're part of the Galar Archaeology Survey. Be Cool, as I've mentioned previously, which is about stars and now exoplanets. We're also involved with the forthcoming Twinkle space mission. And finally, to round off the list, we are involved with various projects translating astronomy into space for enhanced bushfire detection from space, and we might call this a science fiction company, involved with a project to look at the future use of space resources. And as you can see, a key part of what we do at USQ is partnerships. We are working with everyone who's willing to work with us on various research programs. Okay, so Mount Kent is a few hours drive from Brisbane, not far from Toowoomba. It's got sky access. It's an eastern longitude observatory like other observatories in Australia, relatively good skies and great communications to the internet. Compared to Siding Spring, which is what most people are familiar with, it's lower but less windy, which is handy sometimes because we have more consistent seeing. It's not great seeing, but you know, there are not many places in the Australian continent that are really that good. So we tolerate okay seeing for the convenience and flexibility of having a very handy observatory to the campus. Skies are a bit more seasonal. Winter is better in this part of Australia. Some light pollution from Brisbane, the Gold Coast and Toowoomba, but not major. And of course, it's convenient access, which is handy. Okay, moving right along. The projects we have on site, we have at last count 3 telescopes for the Shared Skies Partnership, which does exoplanet stuff and other things. Minerva Australis has 5 telescopes. Song has 2. And I should point out that most of those telescopes are CDK 700.7 meter telescopes. There's a Danish education telescope for which there is no obvious English acronym, but we'll call it FUT. And it's an education facility new on the hill. SmartNet geostationary stuff. And I would point out that all projects are collaborations. And even though we put in literally a dozen big concrete pads, we have nearly filled all of them now with telescopes, I'm pleased to say. So yeah, we're happy about that. Okay, so Minerva Australis is about finding and characterizing exoplanets. It's the Southern Hemisphere equivalent to the Minerva Array in Mount Hopkins in the USA. It's funded by ARC, USQ, our partner universities, mainly in the US. And now I'm pleased to say NASA through JPL have begun funding us because they're buying some of our time on behalf of the US astronomical community. So anyway, we have a collection of small telescopes, 0.7 meters, that can observe multiple planets, well, multiple stars at once, or concentrate our resources. And it's all about doing spectroscopy, radial velocity spectroscopy, to find and characterize exoplanets. Okay, so TESS, for those unfamiliar, which is probably no one, but I'll briefly spend some time in this. TESS, of course, is about exoplanet discovery and characterization. What's different about it compared to Kepler, which everyone knows about, is it's essentially all of sky survey, and it's looking at relatively nearby systems which are more amenable to follow-up study. Okay, so it's a wider and, if you like, closer study. TESS is pumping out so many candidates from its transit survey that Mount Kent and other observatories are very busy doing radial velocity follow-up to find and characterize those potential new and relatively nearby worlds. Okay, so the science case is fairly clear, but essentially it's about coping with the need to have follow-up for TESS candidates, of which there are many. And what we do is we confirm there's a planet, get the mass with the radial velocity observations. We potentially can also search for additional planets. So if there are, essentially, if you can't fit a radial velocity curve to a one planet model, then it looks like you've found a second planet. So that's the sort of thing we do, which means we not only help find worlds, but help characterize planetary system architectures. I will move on. There's a happy Rob Wittenmeyer next to the Minerva Australis spectrograph built in New Zealand by Kiwistar. It's a really nice spectrograph, pleased to say. It's all enclosed these days, so you can't go around and put your hand on it anymore, but that's what's inside the box. Duncan Wright is looking very pleased with himself, as is Jake Clark, one of our PhD students, doing photometry. So we have multiple telescopes, and we have a dual capability to do spectroscopy and photometry as required with exoplanet studies. Moving right along, as I said a moment ago, we can do spectroscopy and photometry as requirements needed. We can do simultaneous radial velocity measurements of one star to get the signal to noise up, or look at 5 different objects at once. And similarly, with the camera installed for photometry, we can do precision photometry at the millimagnitude level, which is what you need to do these days to do any exoplanet work. And so lots of science can come over this sort of dual use facility. In terms of results, the papers are coming out, data analyzed, some public now, of course. There's one example. There's a planet around an F-star, Brett Addison's paper, one of the team members, a postdoc with us. The radial velocity curve there over time. So over time or orbital phase, you get a reflex motion of the star. And as you can see, Minerva Australis is doing quite well in comparison to more well-established facilities on bigger telescopes, Pharos and HARPS. So again, we're very happy with the performance of Minerva Australis. We are delivering the most precise radial velocities in the country. Okay, so briefly then, just finish up on Minerva Australis. We can find planets, we can study them, and with a focus on complementing the TESS candidates. we're getting physical properties out for these planets and capacity, at least, to identify multi-planet systems. More on that later. Talk to me in a year from now, perhaps. We are also, of course, right now looking at the low-hanging fruit, the frequent transits, close, fast orbits, and hot lava worlds, which no one wants to live on, except unless you're Darth Vader. Over time, though, Tess and ourselves will be more able to look at perhaps potentially more benign worlds for life, but time will tell. Okay, Shared Skies Partnership is a long-standing collaboration between USQ and University of Louisville. 3 telescopes, of which 2 are used regularly for transit work. I'm pleased to say we've supported planets discoveries with KELT, and that's the top right, KELT 10b, and at the bottom is supporting a TESS candidate, turning it into a discovery, the object TOI 270 system, Super Earth and 2 sub-Neptune. So that again was Mount Kent observations from one of the Shared Skies telescopes. So, and the one in the picture there is a 0.7 meter CDK 700, which are very cost-effective telescopes, which is why we use them. SONG is new, but we've got some early results. That's the spectrograph, a sample spectrum, and some indications of radial velocity for a test star. Essentially, what we can do there is look at the gentle up and down motion of the star's surface, and that will use to infer the motions inside the star and the structure of the star. So seismology, and it's led by Aarhus University in Denmark, but with an Australian contingent, I'm pleased to say. And a custom spectrograph made in Denmark, working similar to the Kiwi star instrument. And we're getting what we think are the required precisions to be able to do seismology and support exoplanet science. Okay, we're moving right along. Galar is probably a project familiar to just about everyone, but of course it's galactic archaeology with Hermes, the Hermes spectrograph on the AAT. For the most part, it's about understanding the stellar populations and the history of stars in the Milky Way galaxy. So we've been part of that story, helping the Galar project. And what we are doing, though, which is special at USQ, is using the stellar data to infer more precise characteristics for the exoplanet host stars, and therefore infer what sort of planets are going around them. And I'm pleased to say that Jake Clark, who's a PhD student of ours, this is a paper just gone out in the refereeing process right now. This is a simulation showing, in a sense, why it's so important to get your planetary mass and your planetary radius pinned down, because if you get it accurate enough, you can tell whether you've got a genuinely Earth-like world or something quite different, okay? So precision planetary radius and mass measurements there equate to a really important insights into what sort of planet you are dealing with, okay? So this is speaking to us about how important it is to know how precisely your radius and mass are and how they therefore fit the Earth-like worlds in this diagram compared to the other options available. Okay, moving right along, Be Cool is about cool star magnetic fields. It's at least 14-nation consortium led by some folks here at USQ and others. It's about observing stellar magnetic fields using spectropolarimetry, very precise spectropolarimetry, like 1 part in 100,000 precision. And you can not only detect, but map magnetic fields. There's a little movie I'll risk running. You can actually generate, using the Doppler effect and the Zeeman effect, radial, azimuthal, and meridional field maps. We use telescopes like the TBL telescope, Bernard-Liot in Pictamiddy in France, other instruments around the world. We used to use the AAT and may do so again one day if we can get a spectropolarimeter for the AAT. And it not only tells us about the fields, but essentially this type of study where we can map the activity on the surface as well as the magnetic fields. We can study young solar type stars to trace early history of the sun effectively by proxy. We can understand dynamos across a range of stars. We can also, and this is one of our PhD students from France, Alexis Eitzman, working on this with the team, using Doppler imaging and Zeeman Doppler imaging to turn those maps into essentially a systematic error correction. So the more that you understand where the activity-induced jitter is coming from activity maps and from magnetic field maps, the more that you can pioneer the detection and characterization of planets around very young stars. Finally, we can also use the radial field maps combined with the BATSARUS code, the space weather modeling framework, normally used to study the solar wind and solar activity and solar magnetic fields. Doug Evensberget, one of our students actually from Norway, Doug is pioneering work on exoplanetary space weather study. So this horrendously complicated MHD code, BATSARUS, is now adapted to do study stars. And this is one snapshot from his recent work. So unlike what you might think, no, these are not pictures of galaxies. This is a above the star view of the material going off a star that is inferred from the magnetic field data. And what it's showing is a fairly substantive amount of material and strong wind pressure buffeting whatever objects, such as a planet that might be near. This is one of a whole series of Hyades stars. So we're now, unlike other people who are studying individual stars, we're studying whole clusters of stars now in terms of exoplanetary space weather to actually have genuine surveys of exoplanetary space weather and the impacts on planets. Okay, I think I'll move on. If I can get the right button, there we are. Veloce is a UNSW-led project, but USQ is a part of the core team. Veloce is a radial velocity spectrograph, and I guess in a nutshell, we can say that Veloce is sort of like Minerva Australis, except it's, thanks to the 4-meter mirror, able to study appreciably fainter stars than Minerva is suited to. Minerva Australis looks at the brighter stars. Veloce is designed to study in the same way the fainter stars. So it's a Doppler wobble instrument, although Veloce is a general purpose spectrograph, so you can do it for many other things, but it is purpose built for radial velocity studies. What we're doing with Macquarie, Chris Schwab and Macquarie and Duncan Wright here at USQ is, I'm pleased to say, we have ARC funding to value add, as I call it, to Veloce by installing what will be a 0.8 meter telescope from Austria, which will feed light as an auxiliary telescope from outside the AAT into Veloce, so that even when the main mirror is doing galaxies or something, then we will be able to use Veloce as a survey tool, including radial velocity studies. So stay tuned, more on that. That project is really coming to fruition this year. I can tell you more about it next year, perhaps. Okay, so finally, Twinkle Space Mission. It's unusual in that it's essentially a repurposed commercial satellite technology. So the idea is commercial satellites are relatively cost effective. And what you do is, this has been essentially a satellite that's been turned to the stars to do astronomy, but it is a dedicated space astronomy mission. It's University College London has spawned a company, Blue Sky Space, and there's essentially a consortium model built to launch and run the telescope. It's heavily backed by some major players, including the European Space Agency. And one of the things we will be doing at USQ is putting out a call to everyone in Australia who's interested is to get on board, because I think the Twinkle Space Mission is not only great science in terms of studying exoplanet atmospheres and solar system objects. There's also an already very successful educational program called EduTwinkle Run that is essentially about getting high school students to do science with space telescope type data and getting research experience. So when Twinkle is launched in 2024, you can go from simulated or other data to Twinkle Space Mission data being for education as well as research. Okay. Okay, a couple of final slides before we wrap today. I think gazing into the future, TESS should, I think, reach its quota, if you like, of over 1,000 planets found, hundreds of Earth-like worlds, and tens of habitable zone worlds to be found. So I think TESS has actually had its mission extended, so I think it should easily reach its original goals in terms of the sort of planets and the numbers of planets it will find. Of course, a lot of the game is moving into space, and so Twinkle will be not the only telescope, of course. The James Webb Space Telescope, or whatever we decide is a better name for it, will be launched in coming years. Plato, some of you are probably familiar with the Plato space mission, and Ariel. These are all grand exoplanet missions, really. We will see in the next 5 to 10 years, I guess. And of course, we can indulge in some speculation here about the fact that there are people with very deep pockets willing to fund research into the feasibility of sending, ultralight spacecraft with huge ultralight sails and using lasers or the solar wind or some other means to essentially accelerate tiny interstellar spacecraft to do flybys of some of the nearer worlds. Because let's face it, there are some of the nearest stars in the sky have planets, and in some cases, apparently habitable zone planets. So I think there is an impetus and a timescale of a century for missions, interstellar missions to exoplanets. And yeah, it would be good to be so healthy as to expect to be around for those, but it is a waiting game. That will be for the future. Okay, so what do we learn about stars and planets? I mean, let's face it, I think it is appropriate to understand as much about the star as we can, because the story of the star is the story of the planet, including the habitability or otherwise. We know that Earth is in a very long period of habitability, but it will come to an end. In particular, from our point of view at USQ, we need to understand the activity and the winds and stuff, because it's clear that an otherwise Goldilocks world might be uninhabitable thanks to the power of the winds and the atmospheric erosion and all the radiation that may bathe the planet. And for example, there may be habitable zone planets around M dwarfs. But if M dwarfs have enough activity, it won't be a very nice place to live, at least on the surface of a planet around it. Nevertheless, I think I would imagine that the chances remain very good that there is life out there, given the likely huge population of potentially habitable worlds in our Milky Way galaxy alone, and the fact that life is tough, especially the extremophiles, and it's made of common garden variety atoms. So I think the chances of life elsewhere are in fact good. Of course, the hard part is finding it. I think it's much worse than merely finding a needle in a haystack. So I guess, again, we have to be thorough and very patient to expect to find biosignatures, but let's try. As for intelligent civilization, some would argue we haven't found it on Earth yet. Okay, but all jokes aside, I think it is a grand challenge for the future. And I guess you could argue that if ET is trying to talk to you, it's actually easier to listen than to try and find microbes hidden in a distant planet. Time will tell, of course. That is the end. Thank you for listening.
Thanks a lot, Brad, for this great talk. So let us all give a big clap.
Thank you.
Or virtual clap. It was interesting to get both an overview of the field and details on facilities and projects in the fields of stars and planets at USQ. I see we already have a couple of questions in the chat. One by Alexander Hager. So do we observe or have found rogue planets and as mature events, and how many are there?
Okay, the good news is yes, they're actually found. Yes, gravitational lensing is definitely the way to find them. I'm not sure the exact number, but there are tens of them at least. Someone can probably quickly Google the Wikipedia, because that'll give us the best current tally. But these things are found, and people in New Zealand, for example, have long been part of gravitational lensing experiments. So there, the idea, of course, is, again, if you're lucky, you survey enough stars. Every so often, you'll have a lensing event. And so with a background star, the light will suddenly become brighter as the host star gets in the way. But then there's a second lensing event, which means the planet is actually intervening. So that's how you generally can find planets with lensing. Of course, with interstellar or rogue planets, you're just looking for that tiny telltale gravitational lensing event from the planet in deep space. And I must admit, I am very surprised it's so successful, but it absolutely works. These things are found probably in their dozens. And if we look hard enough, it's a reminder how often hapless worlds get ejected from their host planetary system. Okay, and we're lucky we're not one of them, of course.
Yeah, that's
My
true.
question was about from that extrapolating, how many of these rogue planets do we expect roaming our galaxy?
I can't give you a good answer, but I think the simple answer is many. I think that there are a substantial population of them, and in fact, the reason I think we're finding them is that they're so common, right? So all I can do, Alexander, is refer you to recent papers in this area, because I think you'll find that the stats available on existing rogue planets will now give us an idea of how many are likely to be out there. Shall I go to the second question about solar wind carried away most of Mars' atmosphere? Why is there any left at all? If 99% carried away, 100%, right. It's not 99%. Can't quote you on a figure, but what has happened is substantial atmospheric erosion has occurred. It may even be the majority of the atmosphere. But of course, what happens is the solar wind has been decreasing ever since the sun has aged. And so what we have on Mars today is a combination of various factors, including, of course, what would be present based on the CO2 ices and the water ices and other stuff that's there. So that's another driver of how much atmosphere Mars has today. So I don't think it's 99%. It's a lot. But clearly the sun has initially been a substantial influence, shall we say, in atmospheric erosion. It's actually still there today. It's measurable at a very low rate today. So people associated with the MAVIS mission have been able to work backwards as to what it was and what the curve would look like in terms of wind versus time.
So maybe there's some replenishment of some of these things by comets and other debris that fall on Mars, the same way that happens on Earth as well, that we have still small things.
Yes, quite possibly. Absolutely, quite possibly. This is entirely possible.
Okay, thanks.
Okay, shall I go to the next one?
Yes, I see there's another one by
Career in general, informed your views in the uniqueness of our solar system. I would argue that the jury is still out, okay? As I was mentioning earlier in the talk, what has happened is we have found all the low-hanging fruit. We've found all the weirdo, bizarro transiting worlds. We've found the stuff that's easy to find. And we need to be very patient, because I think what the Anglo-Australian Planet Search has shown and others are showing is if you're patient and have enough time base, you find the Jupiter analogs, Saturn analogs. So I would argue that the solar system is in fact not unique. The solar system is perhaps a minority, but it's not completely special. I would argue there are many more solar system-like systems to be found, but we literally have to spend another 10 or 20 years to finding more completely the Jupiter and Saturn analogs.
Yes, I see Rosemary has her hand raised. Please go ahead, Rosemary.
Oh, there I am. Nice to see you, Brad.
Thank you. One and all.
Well, my question's about the Minerva spectrograph.
Yep.
And how you can claim 1 meter a second when that's around what HARPS is doing. Yeah. Actually, the plot you showed looked more like 10 meters a second.
Oh, yeah, the plot was for the early stage, I think. Yeah, you're right. Okay, so let me back up a bit. 1 meter per second is about as good as we can get, and it's not always what we get. That is true.
But how do you get it in any case?
By essentially attention to detail. You have to have an ultra stable spectrograph.
Yeah.
You need the temperature to be controlled.
Yeah.
Ideally, you put it in a vacuum.
And do you?
Yes.
No. Yes.
Yes. Yeah. Yep. We do all that. The Swiss are probably the biggest in this and the most accurate. They have the whole spectrograph encapsulated in a vacuum. But essentially, what you do, right? If you like, the bit that's probably missing here, right, is you have a calibrator. You have something like an iodine cell. You have something which has a fingerprint of lots and lots of spectral lines.
Oh, I know how the whole thing works, but I mean, I'm just curious to know how you get that kind of, precision, given that the HARPS spectrograph is so, like the best in the world except for espresso.
Right.
How you can get the same precision.
Okay, good question. Okay, so I'd go back to the fact that the temperature stabilization is quite critical, right, to within, say, a degree. And the other part of the magic secret sauce here, right, for us at least.
A degree, you mean milli-degrees?
No, the changes that occur thermal are not that critical. What is important is having some sort of fingerprint of many, many lines for which you know exactly what the wavelength is. Because essentially, okay, maybe the best way to say it is we get sub-pixel, hundreds of a pixel precision. So the spectrograph gives you a sense of where, you know where...
But HARPS gets like 10 to the minus 4 or 5 pixel precision, or, you know, like really, really tiny and tiny millikelvin.
Yep.
And pressure is, you know...
HARPS get better than us. That's true. But
they're claiming a meter a second, so...
Yeah, no, we... the most recent figure I saw from Duncan, who's outside the window, can possibly answer this question for you better than me, is I've seen 101.5, and I know from Duncan, he said, yeah, the 1 minute per second is what we were getting in the best case scenario. So, all I can say is we do publish papers where we put in our precisions, and we are happy to share exactly what we do. It's not at all secret at all.
Sure. I mean, it's just astounding.
Yes. Another way to answer your question quickly, because I realize we're out of time, is our secret weapon is Duncan Wright. Duncan is very thorough in his use of the instrument. And I'm happy to offline perhaps have a further conversation about exactly how we do it without the HARPS budget, because I agree. What we're really saying here, folks, is for much less money than the Europeans have achieved a precision which is close and certainly good enough for the work we do.
So I actually had a question related to this. I had a similar question to Rosemary's, but I was wondering if you just do follow-up with Minerva, or you also do new discoveries of planets. Have you had, or you're just starting to do surveys, I guess?
Okay, so we have been for, I guess, at least a year, been doing follow-up work for TESS. We have been getting planet detections. Sometimes, though, often because TESS is public data, we get detections along with other people. So there is, as always with exoplanet science, a race to be first. And while we have got data in parallel with other teams, the hard part is to be ahead of everyone else. And that, I must admit, that is hard. But we are getting there. And there are some discoveries in the pipeline, which I'm sworn to secrecy on, apparently. So ask me a year from now.
Thank you. We have time for one last quick question since we started 2 minutes late. I do have one if no one else has one. So you mentioned how you could map the magnetic field of some stars, I believe the structure of their magnetosphere, showing those spirals. Yep. So is there any hope to detect planets through their perturbation to the stellar magnetosphere?
Yes.
If they have their own magnetosphere?
Yes, yeah, there have been some claimed instances of star-planet interaction, but I think, to be honest, the jury is still out whether that's real. But that is something, we looked at a system called Tau Bu, where we are seeing what's maybe an indication of a planet affecting the subsurface structure and the magnetic field of the host star. So there's papers on Tau Bu by Matthew Mengel et al., his PhD thesis out there.
All right. Okay. Well, let us all thanks again, Brad, for this very great talk and for answering our questions.
Thank you kindly, one and all. We'll see you next time.